Our galaxy, for example, is the Milky Way, and the nearest galaxy to us is the Andromeda Galaxy. We think there are about 100 billion galaxies in the visible universe. The Andromeda Galaxy has been instrumental in reshaping our understanding of the universe and our place within it. For instance, while our galaxy is the Milky Way, the nearest one to us is Andromeda. This discovery provided compelling evidence that the cosmos and the concept of creation don't revolve around Earth. It shattered the notion that the Milky Way was the sole galaxy in existence, suggesting we're just a tiny part of the vast universe. Our knowledge about Andromeda has grown over the last century primarily through observations made on Earth. However, with advanced tools like the James Webb Space Telescope, JWST, now at our disposal, our perspective has drastically changed. Surprisingly, recent data from the JWST has challenged our previous notion about the Andromeda Galaxy, presenting another cosmic puzzle to solve. The JWST has received unusual signals from our neighboring galaxy, leaving the scientific community astonished. Join us as we explore how the JWST received an alarming signal from the Andromeda Galaxy. The perception of the Milky Way has evolved significantly throughout human history, shaped by our developing understanding of the cosmos. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and mythologies. It was often seen as a mystical and central element in the cosmological beliefs of different cultures. In the 1920s, Edwin Hubble, an American astronomer, made a transformative discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Through observations and analysis, Hubble showed that nebulae beyond the Milky Way were actually separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. Andromeda has a rich history of observations dating back centuries. One of the earliest known records of this celestial object can be traced back to the 10th century, when the Persian astronomer Abdul Rahman Alfai described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that Alfai was able to identify this distant cosmic entity without the help of telescopic instruments, relying solely on his keen eyesight and observations. Later, in 1612, a more detailed description of the Andromeda Galaxy based on telescopic observations was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive cosmic structure. In 1764, the renowned French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his well-known Messier catalogue, mistakenly attributing its discovery to Simon Marius, unaware of Alfai's earlier work. For almost 100 years after this, astronomers worldwide were trying to understand more about this mysterious galaxy, each adding to the last one's findings. Before that, Galileo Galilei, an Italian astronomer, revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking observations that challenged the prevailing Aristotelian cosmology. He discovered that the Milky Way was not just a diffused light band, but a massive collection of individual stars, planets, and other celestial objects. Through his observations, Galileo demonstrated that the Milky Way was not at the center of the universe as previously believed, but instead a vast expanse of stars scattered throughout space. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, an original theory or new hypothesis of the universe. According to Wright's speculation, the Milky Way was not a random distribution of stars in space, but a completely flat layer of stars. He also suggested that a portion of this vast structure was our own solar system. While Wright's hypothesis was a step forward in understanding the structure of the Milky Way, it was still limited by the observational technology available at that time. They all still believed that the Milky Way was all there was to it, and considering the limitations, that's not surprising. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when English astronomer William Huggins made a groundbreaking observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical gaseous nebula. This paved the way for the world to really get to know Andromeda for what it really is. Andromeda has a mass estimated to be between 1 and 2 trillion times that of our Sun. It's a colossal cosmic structure that just happens to live relatively close to us in the vastness of space. In all the research conducted until now, scientists believe that Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. Its age hints at a long and intricate history of formation and evolution. One of the intriguing aspects of Andromeda's origin is the hypothesis that it came into being through the merging of several smaller proto-galaxies. This suggests that over billions of years, smaller galactic entities gradually came together under the force of gravity to form the majestic Andromeda Galaxy we see today. Such galactic mergers are common occurrences in the cosmos, shaping the growth and structure of galaxies. For a long time, astronomers thought Andromeda was significantly more massive than our own Milky Way galaxy. From an objective point of view, a mistake like this could easily be made because we're in our own galaxy, and seeing Andromeda from Earth does make things look so large that you'd easily think that there's no way anything could even come close to its size. But that's not the case. Galaxies are immense systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Pinpointing these values precisely is a demanding task that requires sophisticated observational techniques and meticulous analysis. This type of knowledge requires modern tools, which is why the reality is just coming to light now. Recent research has brought about a reevaluation of these beliefs. New findings have led scientists to somewhat reduce their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. As a result, the current understanding is that the masses of these two cosmic giants are much closer than previously thought. The Andromeda Galaxy's physical dimensions, though, are what astronomers totally agree on. It stretches farther than our own Milky Way, with an impressive diameter of about 220,000 light-years. Andromeda surpasses the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years, making it a truly significant cosmic entity taking over a large region in space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. In the heart of the Andromeda Galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow elliptical paths similar to planets orbiting the Sun in our solar system. At a certain point in their elliptical orbits, stars come closest to the black hole, known as the perihelion. At the perihelion, the gravitational forces are at their strongest, causing the stars to move at their highest speeds. This is when the stars bunch up and become more concentrated in space around the black hole. As they bunch up, the stars release energy in the form of radiation, including visible light and other types of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galactic core of Andromeda's active galactic nucleus, AGN. An active galactic nucleus, popularly known as an AGN, is a highly energetic region at the center of a galaxy. It is characterized by intense emissions across various wavelengths, from radio waves to X-rays. AGNs are powered by the presence of a supermassive black hole at the heart of the galaxy. These supermassive black holes are incredibly dense regions in space where an enormous amount of mass is concentrated within a very small volume. When astronomers observe active galactic nuclei using advanced telescopes like the Hubble Space Telescope, they notice a very interesting phenomenon. One of the most fascinating features of the Andromeda Galaxy is its AGN. It appears to have 2 points of concentration, meaning there are 2 distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding areas. The brighter concentration is the second point of focus, which is just slightly off the true galactic center. Within this area lies the supermassive black hole, the mass of which has been estimated to be between 11 to 23 million times the mass of our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way. As a result, they play a crucial role in the evolution and dynamics of galaxies. When matter, such as gas and stars, gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various wavelengths, which is why the AGN is highly luminous. When astronomers observe the AGN of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature is a result of the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda Galaxy also has another super interesting feature: an abundance of globular clusters. These globular clusters are tight groups of stars that orbit around the center of the galaxy, kind of like satellites revolving around a planet. Andromeda is estimated to harbor around 460 of these globular clusters, which are densely packed with stars. Some of the most massive clusters in Andromeda include the famous M2, also known as G1. Is about 2.5 times more luminous than any globular cluster in the Milky Way. G1 is not just a massive globular cluster, but also intriguing due to its complex structure and unique characteristics. G1 is situated at a considerable distance from the center of the Andromeda Galaxy, about 130,000 light-years away. It is thought to have a total mass of around 4.5 million times the mass of our Sun. For comparison, one of the largest globular clusters in the Milky Way, Omega Centauri, is around 10 times less massive. This suggests that G1 is an ancient structure that has remained intact for billions of years. G1's sheer size, mass, and position within Andromeda are also quite telling. The presence of G1 and other massive globular clusters provides valuable insights into the formation and evolution of the Andromeda Galaxy. One possibility is that these clusters formed early in the galaxy's history during its initial stages of formation. G1 and similar clusters may have formed as independent dwarf galaxies that were later captured by Andromeda's gravity and became part of its stellar population. But there's more. The JWST, being a remarkable tool, has contributed to some groundbreaking discoveries. While we know Andromeda is home to hundreds of billions of stars and potentially even more exoplanets, the JWST's findings have significantly advanced our understanding of its secrets. The JWST has successfully spotted and studied water vapor in the atmosphere of a distant exoplanet within Andromeda, marking a major milestone in exoplanetary research. The presence of water vapor is significant because it suggests the existence of liquid water, a crucial element for life as we know it. Now, what about the strange signals detected by the James Webb Space Telescope in the Andromeda Galaxy? While studying the exoplanets, the telescope detected an unusual signal originating from a distant corner of the galaxy. The signal was a series of regular pulses unlike any known natural phenomenon. Initially, scientists thought it might be a glitch or interference, but after careful analysis, they realized the signal was indeed coming from the Andromeda Galaxy. When scientists first discovered these regular pulses from a distant corner of Andromeda, they initially speculated about potential sources. A leading hypothesis was that the pulses might be related to a new type of pulsar, a type of neutron star that emits beams of electromagnetic radiation as it rotates. However, the regularity and specific characteristics of the pulses didn't quite match known pulsar behavior, leading scientists to consider other possibilities. Some propose that the signals could be the result of highly magnetized neutron stars interacting with their surroundings, but this idea was eventually set aside due to a lack of supporting evidence. The Andromeda Galaxy is not only a fascinating subject due to its size and proximity, but also because of the insights it provides into galactic dynamics and evolution. One of the notable features of Andromeda is its interaction with the Milky Way, which is expected to culminate in a dramatic collision in approximately 4.5 billion years. This future galactic merger is often referred to as Milkomeda or Milkdromeda in scientific discussions. Such events are crucial for understanding the long-term evolution of galaxies, as they significantly alter the structure and star formation rates of the involved galaxies. The interaction between Andromeda and the Milky Way will likely trigger a new wave of star formation as gas clouds collide and compress. This cosmic event could reshape both galaxies into a single, larger elliptical galaxy. Observing the precursor interactions and dynamics of Andromeda provides astronomers with valuable data to model and predict the outcomes of such massive galactic collisions. Additionally, Andromeda serves as a natural laboratory for studying dark matter, a mysterious and invisible component that influences the gravitational forces within galaxies. By examining the motion of stars and gas in Andromeda, scientists can infer the distribution of dark matter and improve our understanding of its properties. Recent studies have also revealed that Andromeda has a complex system of satellite galaxies and a vast halo of dark matter, which are essential for understanding the formation and evolution of large galaxies. These satellite galaxies, some of which are similar to the Milky Way's own satellites, play a role in the accretion of matter and the overall growth of Andromeda. The detailed study of Andromeda not only enhances our knowledge of galactic structure and dynamics, but also helps us to place our own galaxy within a broader cosmological context. As research continues, the Andromeda Galaxy remains a central focus for astronomers seeking to unravel the complexities of our universe.